and wait for confirmation it's actually streaming. So I got it. You guys cannot see it, but there's a little green box, down there that says, I'm actually connected now. So we are all good here. All right. So I want to show you guys where to find all that stuff, on YouTube. What you're seeing here is not what you will see because this is my channel. It's an inside view of my channel. So since you cannot sign in as me, you won't see this part here. So let me start a new instance of the browser, incognito, new private window. So this way it is not signed in any particular way. So it will resemble what you would find. So you just go to youtube.com and you type some profs, okay? SOMEPROFS, okay? So that's pretty much the only thing you need to write down. I think the link is in the syllabus as well. So if you read the syllabus, you will be able to find this link as well. Press the enter key, and this is, this is the channel. Click on videos, and it will list all the recorded videos in a reversed chronological order. So the more recent video clips or lectures will be listed first, but you can go back time all the way to 2010. So I got about 9 years of recording, on YouTube, okay? And each video clip is usually labeled the way it is here, which is the year, month, day of the recording, and then which class it's for. I have yet to teach a class where I have multiple sections on the same day, so that is not an issue. So for this class, you just have to look for a date that is a Monday or a Wednesday. That would be your video. Now, does it mean that you cannot watch the ones from Tuesdays and Thursdays? Absolutely not. If you want to watch the Tuesday, Thursdays ones, it's not a problem for me. All right? So for those of you who do, you will notice that I do teach the class slightly differently, between the Monday, Wednesday class and the Tuesday, Thursday class. Not so much it was a conscious effort to make it different. It's just that different things pop up in my mind, so I teach it slightly differently. Okay? All right, so if this is done, I'm going to close the incognito window and then go back here. And one way to confirm whether the recorder or the streaming is on or not is for me to look at what is being streamed. And it doesn't, actually it does. So it does show that this is being streamed and we are live, actually live. But because it's unlisted, you guys cannot access it until I make it public. So are we good so far with all this stuff? Okay. So I'm going to close this window and close these two, and then get back to Canvas. And this is the Monday, Wednesday class. This is the wrong one. I'm going to go back to Monday, Wednesday. There we go. All right. So what we'll do is we're going to start with this link here, which links to a document, hopefully. No, it doesn't do that, does it? Okay, now it opens it. That's interesting. Okay. So this is the module. I named these, each of these kind of short presentations as a critical module. And I did this way, way, way before Canvas. So this kind of module is not the same thing as a module in Canvas. You can look at this as a sub-module, if you will. And let's magnify this a little bit. All right, so what we'll do is we're going to start with physical states. This is not a physics class, so we're not going to get too much into the actual physical states. But we'll start with these things because the way I want to teach this class is from the ground up. So we start with the most concrete actual things, like things that you can measure using a voltmeter, or you can look at using a oscilloscope, and then we'll work our way up to things that can compute. things that can add, things that can subtract, compare, and then we'll work ourselves up to processors, and then assembly language programming, and then to C programming, but expressed in assembly language constructs. So that's how this class is going to proceed. Is we start with the very lowest possible level stuff first, and we go from there going up. Do we have any questions about the general direction of this class? Okay, if there are no questions, we're going to move forward here. All right, so the first type of physical state I want to talk about, or mechanism for a computer, is electromechanical. So before we have electronic computers, which we all do use now, we have electromechanical computers. So what is an electromechanical computer? It's a device that has both mechanical aspects, like things that can rotate, things that can actually mechanically rotate, and also things that are electrical. So what we are rotating is a plate of contact points. So by rotating a disk, by changing the contact points or how things are connected, you are basically doing quote-unquote computation. But the simplest electromechanical device is a relay. And we still use relays in vehicles and buildings and HVAC and stuff like that. What is a relay in electrical sense? Does anyone want to kind of jump in and explain that? No? Okay. I can show you one. So let's go check out a relay, automotive relay. And here's one, okay. So this picture is the picture of a relay. So the way a relay works, okay, this is the schematic, what we call the schematic of a relay. And you can see that it has got two contact points here, one contact point here, and one thing kind of in between here. Can everybody see the numbers on this picture? Or should I magnify that a little bit? We're good? Okay. So with a relay, what happens is the thing between 86 and 85, the bottom device, that's an electromagnet. Okay. So with an electromagnet, it means if current is to pass through the electromagnet from 86 to 85 or the other way around, then it will generate a magnetic field. Is that okay? So what are we doing with the magnetic field? The electromagnet is physically disconnected from the other stuff in the relay. So what happens here is, see this little kind of slanted line here? It's a reed, okay? It's something that can actually move, okay? At this point, okay, ignoring the electromagnet at this point, what is the connection? Tell me which 2 points are electrically connected as it is shown at this point. It's between 87A and 30. Is that making any sense? The picture basically says, well, this point here can go through this slanted line, which is something that can actually move, and it connects to point 30. Are we good so far? Okay. Now, if the electromagnet is energized, which means it generates a magnetic field, this part here, this slanted line, is made out of ferrous material, which means it can be attracted by magnetism. Is that okay? And it's spring-loaded to go up. So what happens when the electromagnet is energized? What do you think is going to happen to this part that can move? Exactly, it gets pulled down. Okay, very good. So then point 30 is no longer connected to 87A, right? And instead it will be connected to 87. Very good. That is an electromechanical device. The electro part has two aspects to it. The first one is the magnet itself is electromagnet, which means it is energized by electricity. The second part is what we are switching is also electricity. So the electro part specifies how you control the device and what it is controlling. The mechanical part describes the mechanism by which it changes which point is connected. So because it is actually physically moving this slanted line, which is just an actual plate somewhere inside the relay, it's mechanical. And as a result, the device is called an electromechanical device. Are we doing okay so far with this? All right. Now, there are several other names also for 87A. 87A is what we call an NC, it's called an NC point, which stands for normally closed, okay? And then 87 is an NO point, which stands for normally open point. Normal means the magnet is not energized. If you just leave the device on its own, not connecting it to anything, then 87A is connected to 30, which means that circuit is closed. So when we talk about circuits, closed means connected, open means disconnected. So do we have any questions about those terms? Okay, we'll use those terms again. Yeah. Yes. So 87A in this case is NC because it's normally closed, or you can look at C as connected as well. And then 87 is NO because it's normally open. Open means disconnected. Yes?
What does normal mean?
Normally means not energized. So when the magnet is not energized, it is quote unquote normal. So very good. I like those questions. Are we good so far? All right. So early day computers are made out of stuff like this. Okay. So when the electromechanical computer operates, you can actually hear it operating. Okay, because relays and routers and stuff like that, when they turn, when they actuate, they make sounds and lots of sounds. In which movie do we see electromechanical computers? It's a fairly recent movie about a pretty important person in the history of computer science. Yes?
Was that in World War? Was it Enigma? Yeah, Enigma.
Enigma. From which movie?
I think, I don't remember the name of movie, but I remember all of this stuff.
Okay, go ahead. Yep, exactly. Yeah, go ahead. Oh, okay, all right. But you got it too, right? An imitation game. Yep. So in that movie, they talked about Alan Turing, which is considered the father of computer science, and the computer he was putting together to decrypt German encrypted messages was an electromechanical computer. So if you watch very closely at the computer itself, you will see rotors turning, and then you will see mechanical parts moving and stuff like that, because it was an electromechanical device. So are we doing okay so far with kind of these concepts? And if you really want to take a look at that device, I suppose we can look for it. Okay, Alan Turing, B-O-M-B-E. So we want a picture, or there we go. And this is an even better one. So it's made out of a lot of rotors like this, and then the rotors turn because of electromechanical components. So this is a good picture. It kind of tells you about the size of the whole thing, and how much processing power do you think it packs? Very little by today's standard. Okay, if you have a Fitbit, your Fitbit can probably run circles around this at high speed. Okay, but at the time, this was the best technology they could use, and it still beats humans, right? Because the whole idea of using a computer to do the decryption was because the Germans introduced another disk into the Enigma machine, making the possible combinations big enough that humans cannot practically crack the code. Now, when I say practically crack the code, it simply means by the time humans can crack the code, by the time the British people can crack the code, it's already useless. The military operations is already done and it's already over. So that's the reason why they have to use a computer to do what people do, in terms of decrypting the messages. Is that okay? If you have not seen that movie, I highly recommend that you watch that movie, but from the perspective of computer science. Okay, how everything started in computer science. All right. So can someone kind of think of a few limitations of such a device, an electromechanical computer?
The mechanics are big. I mean, the mechanical parts are big.
The mechanical parts are big. Yes, go ahead.
The more moving parts you have, the more likely one will fail.
So there's a chance of failure. Yep, because of movements. Yep. You first, and then you. Go ahead.
Friction.
Friction. So it's not energy efficient. Go ahead. Yeah, go ahead.
If you put two relays close to each other, can the electromagnetic fields interfere with each other?
Potentially, you can have interference, but you can increase the distance so that the magnets do not interfere with each other. Yep.
It can be difficult to repair because there are so many moving parts.
There are many, many moving parts. Exactly. When you look at that picture, did you see a huge shaft here at the bottom of that machine? Can you just kind of imagine how much torque it needs to turn that particular shaft, which in return turn all the rotors? So yes, so all of that is correct. Okay, it is slow because it's mechanical. It is inefficient because the devices are big. The electromagnets consume a lot of electricity. So there are a lot of kind of disadvantages to a electromechanical computer. But since that was the only technology that existed at the time, that wasn't a choice. Okay, they cannot just say, oh, we can use something else. All right, so moving on to the next level of technology, vacuum tubes. Okay, so all of these hyperlinks are kind of live. They're kind of interesting if not required. So when you click on this one, it will go to Wikipedia that talks about vacuum tubes. This is not a physics class. I really do not care whether you understand how a vacuum tube works or not. But there is a description in this page as well as on my page of how it works. So when you look at a vacuum tube, okay, and this is where I can try to draw a picture using my stylus. So give me a moment to set this up first. I need Zerno, which is under accessories. There we go. So think of this as your whiteboard. So everything that I draw here is also recorded. So there's no need to copy everything here except for the stuff that you think is relevant and you want it in your own notes. Okay. So when we look at vacuum tube, okay, there's an enclosure, and inside is vacuum. Okay, so there's very little air. Okay, there's no true vacuum, but there's very little air inside this enclosure. Okay, and at the center of this thing is a filament. Okay. So the filament is kind of like an old style light bulb. There will be a point, when I teach this class, nobody understands what a light bulb is, like a real traditional light bulb, the ones that gets hot, okay? Because LEDs, I mean, fluorescent CFLs, okay, compact fluorescent tube light, are already replaced by LEDs. But in the good old days, we have heating filaments, okay? It heats up and then it glows and, it gives you light, okay? So vacuum tube has kind of the same thing. And then on the outside of this thing, there is a mesh. Okay, so if you look at the cross section, this is what you will see instead of the mesh. So it's got some openings. And then on the very outside is kind of like a solid, cylinder. So remember, we're trying to look at this picture as a chopped picture, of a vacuum tube. So we have the three components in this case. This is called the collector. This is called the, I'm trying to remember. I think this is the emitter, and that would make it the base. I could be wrong here, so don't quote me. But the idea is, when you heat up the emitter, when you heat up the filament, electrons are no longer, the atoms don't hold on to the electrons tightly anymore. Okay, so normally the atoms will try to, the nucleus of an atom will hold on to the electrons pretty tightly and don't want to let go of the electrons. But when things get heated up and energized, the nucleus says, oh, well, I suppose we can go around a little bit. So now the electrons are kind of free moving. They can kind of move around on them, on their own. And the emitter is going to be charged negatively. So there's a negative charge, with the emitter. And so now electrons are ready to leave the filament. But they're not going to leave unless there's a reason to leave. So what happens is the mesh is going to have a charge in it. So when the mesh has a charge, like a positive charge, then the electrons that are free to move is going to say, oh, I want to go over there, because opposite attracts. So negative charge, which are our electrons, wants to go to where a positive charge is. But except this is a mesh, so electrons can actually go through the mesh and end up landing on the collector. And this is how we can control whether electrons can land on the collector or not, by controlling the charge of the base. Is that okay? So it's a switch. It really is just a switch. But how is this kind of switch different from a relay? Which part is missing? Yes? There's no movement, okay? Except for the movement of electrons, right? But there's no mechanical movement of any kind. So, and it can also be done, so it's faster because you don't have to wait for something to move because of magnetism. So it's faster. It still consumes a lot of energy because remember, the emitter has to be heated up. So that still takes a lot of energy to heat up the emitter. But it will last longer because we don't have actual mechanical movement. But it will fail. It will fail eventually. Can anyone imagine how vacuum tubes fail eventually?
Glass breaks.
The glass breaks. Okay, go ahead. The filament burns out. Very good. Okay, and there was a third hand too. Oh, okay. But you can add to it if you want to. How does a filament burn out? I mean, it doesn't seem to make sense, right? I mean, it's a piece of metal. You pass a certain amount of current through it. It heats up, it emits light, and that's the end of the story. How does it possibly burn out? You got your hand up first. Go ahead. Yeah.
Yeah, I'm just thinking the heat expansion and contraction, getting hot and cold.
Not quite that. It is a process called, it starts with an S for those of you who have taken a physics class. It is a phase change. Sublimation, very good. Okay, so sublimation refers to a phase change from solid to gas directly. And as it turns out, metal will sublime, under certain conditions, like when it's under a lot of heat. Tungsten, which is usually what this filament is made out of, tungsten would actually sublime. It would turn into a gas, okay? And the gas would go to the outer part of the vacuum tube where it's cooler, and it will condense back into a metal. And that's why, in the good old days, well, even now, I mean, how many people have a car that still has a halogen lamp? Like a headlight that's still halogen lamp based, okay? When it does burn out, what do you notice? On the outside, it's kind of dark, right? It's because the tungsten has sublimed and it has deposited itself around around the glass. Okay, and that's how vacuum tubes burn out normally. Okay, so it does burn out. Okay, so that's vacuum tube. It's a step up from electromechanical devices because there's no physical movement. Things can go a lot faster, but it still consumes a lot of energy because the emitter still needs to be heated up. Okay. So are we still good so far? Okay. But what you need to remember here is it is really just a switch. Okay. Look at this as a complicated switch that also glows. All right. So switching back to the notes here, and I'm here. Okay. So after vacuum tubes, are transistors. Okay. So a transistor is made out of PN junctions or semiconductors. Okay. So I will just give you a kind of rough idea of what it means. Okay. What is a semiconductor? So I'll switch back to here, and we'll move this array, and we'll look at a basic PN junction. Okay. What is the primary material or element used in semiconductors? That element is part of the name of a region around here. Yes? Not copper. Silicon. Okay, not silica, but silicon. Okay, so silicon is an element. Silicon as an element has got 4 outermost electrons in its orbits. And so, it can form a crystalline structure just like carbon can. Okay? How many people know that carbon has a crystalline structure or can have a crystalline structure? Okay? And obviously that is not the structure as it is in your pencils. As the lead in your pencil, it is graphite, and graphite is not exactly crystalline. How do we call the crystalline form of carbon? Diamonds, okay? So do you think diamonds conduct? If you try to apply electrical charge to one end and the other end of a piece of diamond, do you think it will pass through? Nope, it does not pass through because it's a crystal and the electrons are kind of locked in place. Okay, silicon is kind of the same thing. It has got 4 outermost electrons in the outermost orbit, so it will form a structure similar to diamond. And as a result, silicon itself is not a conductor. Okay, so you can kind of look at silicon Si like this. Si connects to another Si here. It connects to another Si over here, another Si over here, and another Si over here. So all 4 arms are now used. You do not have any free electrons going around. If you have not taken a chemistry class, this is representing something that's sticking out of the plane that you're looking at, and this is representing something that's going into the plane that you're looking at. So this is kind of like a 3D thing, where you have a base of 3 things, a center, and something that's on top of it. Okay? So semiconductor becomes semi-conducting because of the doping process. Okay? What the doping process does is introducing what we call impurities into the silicon. Okay? Depending on what you introduce, like phosphorus, as opposed to, I cannot remember the other one, germanium. Okay? So depending on what you're introducing into it, for instance, if you introduce okay, I need to cheat a little bit here and look at my notes. It does not say, okay, fine. So if you replace this with what we call a P-type material, so P does not represent phosphorus in this case, but it's a P-type material, then it will introduce a concept of a hole, because a P-type material only has 3 electrons in its outermost orbit. But because it is the minority within the majority of silicon, it's forced into the structure of the crystal. So that means we have a concept of a hole. But a hole is kind of interesting because it's simply saying that there's no connection here. Something is missing. And that hole, which is basically the same thing as a positive charge, can move. And when the charge can move, the material conducts. So a p material conducts like this. On the other hand, if you replace the p material with what we call an n material, then you have a free electron around, because an n material has 5 outermost electrons in the outermost orbit, but the structure only is going to take up 4. So now you have 1 electron left over that has nowhere to go except to kind of float around a little bit. Okay? So once again, you have a negative charge in this case that can flow around and go places. And once again, your material becomes a conductor because you have a charge that can move. Okay? So now, when you look at a p-n junction, one side is a p, the other side is an n. In other words, this is, for the most part, silicon, except this part is doped with p-type material, things that are missing 1 electron. And then the other side is basically the same thing as silicon, but it's doped with n-type material, where there's a free electron moving around. So now the question is, well, what happens when I try to connect a charge, positive charge on one side like this, and a negative charge on the other side? What's going to happen? Electrons, which is originating from the negative side, will try to go in this direction. Okay? So the question is, what happens right at this border? So as it turns out, the electrons will actually go through, okay, because we are in, this is what we call a positive bias with a p-n junction. Okay, so in this direction, current can go through. Okay, so we'll just draw a picture here. What if I reverse the polarity? Okay, we have p, we have n, but this time we have negative and positive here. Well, as it turns out, no current will pass through in this case, which is a little bit puzzling, because if you look at the p material by itself, it conducts. When you look at the n material by itself, it also conducts. So how come in this case it is not going to conduct? Yep.
Because it doesn't want to move towards the electrons aren't going to want to move towards the n side because it's already negatively charged. They're going to want to move towards what's positively charged.
Yep.
There's no incentive for the current to flow.
Because of this. Because the interface between the two material, the negative charge here is going to, quote unquote, suck the holes to this side. Okay? So when the holes are being sucked to that side, there will be a region of the p material that is no longer a p material anymore. In other words, the holes are now missing. If the holes are missing, you don't have any charge that can flow, and it doesn't conduct anymore. The other side is kind of the same thing. This positive charge is going to attract electrons to this side, which means there will be a region here where even though you have elements that should have 5 electrons on the outside, the extra one is not there anymore. So once again, you don't have a free moving charge anymore, and as a result, this region of the n material is also not conducting. So now you have 2 regions, okay, one to each side of the p-n junction that is not conducting, and as a result, there's no current passing through anymore. So that's the basic, working of a p-n junction. I am not an electrical engineer, so when you go to a 4-year university and you take device physics, you'll get a much better treatment of what I just said. Is that okay? All right. So now, as far as we are concerned, what is of concern to us? I mean, why do we need to know all of this? All we need to do, or what we need to understand, is how do we make a switch out of this, right? Because the whole idea of a computer is made out of a whole bunch of switches. So now we just say, okay, let's just say that we have a funny way of combining these p-n junctions and whatnot, and turn it into a switch. Okay? And there are 2 types of switches that we are most concerned about. So a switch, which is a transistor, kind of looks like this. Okay? And the other one looks like this. And I think there's an arrow going in one direction, so let's see. I'm gonna cheat a little bit here and go back to my notes. Okay, that's an N transistor. There we go. And here's a P transistor. Okay. So now we have two transistors. One is called an N transistor. The one to the left is called an N transistor. Yes?
I thought the arrows were opposite.
I'll explain that later. Okay. So this is an N transistor on the left, and this is an N transistor, a P transistor on the right-hand side. What is the difference between the two? The bubble, right? The little circle thing. Yep, you're right. The little circle thing is the only thing that you can visually differentiate between an N transistor versus a P transistor. Okay? Remember how we want to look at things as switches, right? So the control of the switch is this part here. This is called the gate, okay? So we'll label the gate here. And you can see the arrow going from one end to the other end of the kind of crooked line, right? So the direction of the arrow indicates source to drain. So it always goes from source to drain, goes from source to drain. Are we doing okay so far? Yes? Okay. So this is the weird part, okay? With an N transistor, the source is always something that has a negative charge to it, okay? It is connected to a negative charge to the source. And with a P transistor, the source connects to a positive charge. You can kind of imagine one is, okay, so the N transistor is always having one end connected to a positive pressure, okay? Whereas a P material has the source connected to a negative pressure compared to, like the room pressure. Is that okay? The gate is your control. The gate says, well, do we want to open up this valve so that the drain connects to the source? And it's the same terminology as the other one. The gate is also controlling whether you want to connect the source, but in this case, a positive charge to the drain. So it is a switch. The gate is the control of the switch. And you're asking a question of, do I want the drain to connect to the source? That's the question. Okay, so if everything is about the same, what about this little bubble here? So the bubble is important because in the case of an N transistor, when the gate has a positive charge, that turns on the device. It completes the circuit. So I'll write it down here. Okay, so I'll say positive gate connects source to drain. That is the case for an N transistor. With a P transistor, this little bubble thing here, you can look at it as negation, as in not, okay? So in this case, it is the opposite. So a negative charge or negative gate compared to source connects source to drain. And that's it, okay? So from the abstract perspective, from our software perspective, this is how we can describe an N transistor versus a P transistor. Do we have any questions about these two? Yep.
I got a disconnect. How many semiconductors are made out of a transistor? Like, we went from a semiconductor.
Right.
How does that translate?
Okay, so each one of these transistors is made out of, it doesn't have a p-n junction in it. each one of these is called a field effect transistor. So the application of a voltage potential at the gate instantaneously creates a zone within the material that can change whether it is conducting or not.
Oh, okay. So
Yeah,
it's
but
not
it's
exactly the same. It's
not exactly the same. Yep,
the concept.
correct.
Okay.
But it does make use of the concept of p-n junction. It's just that it's not the material are not physically connecting.
Gotcha.
Yep, it's based on the field effect, which is just a capacitance kind of effect. Yep.
So we're talking about two different transistors, and the only difference is the default state, one that's always connected and the other one is not.
So with these transistors, the default state is always, you can assume it is not connecting. Okay? So the only time it connects in the case of an N transistor is the gate has a higher voltage compared to the source. If it is not, then it won't conduct. Yes, go ahead. Yeah.
How do they calculate the gap
The
between
gap.
the gate and the other for the voltage, or not the voltage, but the transistor? How they calculate the gap, like how big of a gap? Because you said they don't connect. The gate isn't physically connected to the other
Oh,
material.
that's a very good question. Okay, so you're talking about this little gap here. Okay, that gap is now in single digits of atoms thick.
Okay.
So that's a very good question because go ahead.
Does it get stronger if it was closer, or weaker if it was further away? I'm assuming.
Okay, that's also a good question. When this gap is bigger, then you need more charge at the gate to switch whether to control whether you want to connect the source to the drain. Is that okay?
Yeah, no.
So, and when it is closer, then you don't need as much charge to control whether you want to connect the source to the drain. So that's one thing about transistors, because in the past, I cannot remember how many years. So initially, transistors have a really thick insulator between the gate and this particular part of the transistor. So it takes like 5 volts to switch, okay? But as the transistors get smaller and smaller, and what enables transistors to get smaller and smaller is they make this gap smaller and smaller too. So now they're now in single digits of atoms thick, which is amazing, okay? And it becomes so thin that quantum effects kind of comes into play. Well, so what kind of quantum effects do you think we're dealing with here? Okay, so yes, you're correct, but I think go ahead.
Are you talking about like superposition?
We're talking about electrons not really being a particle, as in it continuously go from one place to another place. Okay, so now since somebody asked a question, I'm gonna go answer that question a little bit. What is your mental picture of an atom? There's a nucleus, okay? Let's just think about the hydrogen atom, okay? Hydrogen is easy because the nucleus is just a photon, and a photon has a positive charge. So in order for a hydrogen atom not to be charged, it has an electron on the outside, right? One photon and one electron. So what is the mental picture that most people have of a hydrogen atom? Okay, here's my proton that has a positive charge. And here's my electron going around the proton in an orbit, right? So when we think about orbit, we think about satellites. Okay, satellites go around the Earth like that, right? Not exactly when we look at things that small. Okay, so as it turns out, first of all, it's not a track like this, because it's in 3D space. So what we call the orbit of an electron is actually not flat. It is not a line. Instead, it is a sphere. It's the surface of a sphere in this particular case. Then you have a big question. How do you make something orbit around a sphere? instead of a plane. It doesn't make sense. It does not make sense at all. And then the other thing is, when you observe, electrons, as quote unquote orbiting around a photon, it suddenly disappears from one spot and reappearing at another spot. It does not move continuously. It just pop up here, disappears, reappear, disappear, reappear, and so on. Are we doing okay so far with this? Yes, more or less? Okay. So do you think the pattern of the electron disappearing and reappearing is really just a sphere, an infinitely thin sphere being a surface? It's not. It's a probability distribution. In other words, there's a probability. So it's hard to look at it when I don't have the right props. But okay, think of my head as the proton. Okay? And there's an imaginary sphere, which is the optimal place the electron will appear. But even though that is the quote unquote optimal place, let's say the optimal place is about this far away from my head, okay? And imagine that this is I'm just defining the radius of a sphere around my head, okay? So even though this point is optimal, well, sometimes electrons can appear closer to me, and other times it can appear further away from me, because it's probabilistic. So as we get closer and closer, it gets less and less probable. As we get further and further away, it also gets less and less probable, but not impossible, okay? So when you think about it that way, if this gap becomes really, really, really small, then there's a chance that the electrons on this side that belongs to the gate can reappear because of quantum effect on the other side. That becomes a problem because now we have a leakage of current from the gate to the other side of a field effect transistor. That is the limit of how small we can make transistors. Because we cannot make this gap so small that electrons can just reappear on the other side. Yes, go ahead.
I'm assuming that grounds it then.
Huh?
I'm assuming that grounds it then. It makes it ineffective.
It makes it ineffective, correct? Because now you have current going through here, and the field effect is gone. It's no longer a charge, a field that is changing the behavior on this side. You actually have current going from here to here, which destroys the property of a field effect transistor. There was another hand. Go ahead.
What do you think the solution is? Haven't we already come to this point? Where we're supposed to
We have come to this point already. So we cannot make transistors much smaller anymore, but we can make 3D transistors now. So instead of having, instead of looking at the circuit on the chip as a two-dimensional thing, we can look at it as a three-dimensional thing. The walls of what we usually see as just layers of material, the walls can also have transistors now. So we can pack more transistors into a smaller area, even though each transistor is still about the same size as before. Okay? Now, this is actually, and I know some of you will think, but this is not a device physics class. It's not a physics class. Why are we talking about this? It is actually very important. Okay? What is the difference between a computer today, any computer, any watch, any mobile device today, compared to, let's say, 10 years ago? Size. Okay, go ahead.
It has billions more transistors.
Well, yes, but let's just focus on specifications of the device itself to consumers. Okay, to most consumers, what has changed over 10 years? Yes. Speed. Okay, processing speed. Right. Processing speed has increased. What about energy consumption? Do you think it stays about the same in the 10 years, or do you think it's much better today? It's much better today. Okay. What about the screen size, the resolution of screens on cell phones? Has that improved over the past 10 years? What about the resolution of cameras on your cell phones? That has seen insane, progress over the past 10 years. I mean, if you look at a professional digital SLR 10 years ago, the pictures that you can take is no better than the cell phone today. And we are not even talking about $1,000 cell phone. We are talking about maybe a $300-400 cell phone. And the digital SLR back in those days is like $6,000. So now the question is, what makes that possible? Transistors, but one particular aspect of transistors. Yes?
Make more of them in a small area.
The shrinking of the transistors. Okay, so the shrinking of the transistors lead to several consequences. By being able to pack more, you now have higher resolution of, let's say, cameras, right? And you can pack more transistors to do processing, so you have an increase of processing power. But because it doesn't take as much of a charge to turn on and turn off the devices, you also have a lowered power consumption. So now, why is that important to you? You're in this class because what do you want to do in the future? Some of you are programming, and some of you want to design processors, right? Some of you want to get into electrical engineering, computer engineering, computer science, and all kinds of stuff like that. So let me ask again, why is this important? Why do you want to know the trend of things? Exactly. Not so much predicting, but you know where it is going to be when you graduate. Okay? Why is that important? I keep asking that. Yep.
So you're not designing something that's going to be obsolete in 10 minutes?
That's one, okay, but that's one. But knowing that we will have a lot more processing power available by the time you get your bachelor's degree or master's degree compared to today, things that are difficult to do today because we don't have enough processing power may become possible when you graduate. Is that making any sense? Or if you think about it, things that will take too much device and it's going to be too big or consumes too much power by today's standard, by the time you graduate, maybe it will be miniaturized enough and it will consume less power, or it will consume, the power it consumes will be small enough that it becomes practical again by the time you graduate. It opens up possibilities, and if you can think about all of those possibilities, you can kind of plan ahead of time better. I don't know whether that makes sense to you or not, okay? But the way things are changing, is at an increasing rate. We can no longer predict what type of occupations are going to be available when you graduate. Yep.
So where do you get news about this sort of thing?
Say that one more time.
Where do you get news about this sort of thing? How would you stay more aware of that?
That's a good question. How do you stay abreast with advances in technology and whatnot? There are a few websites you can kind of keep an eye on. One is /dot. It's /dot.org. And as you can tell from its subtitle, News for Nerds, Stuff That Matters. Okay, this is one place. It's kind of like a clearinghouse of stuff, that relates to nerds and geeks and people who like technology stuff. Okay, it's kind of varied. They vary, but starting from here, you will see that sometimes they quote from Wired. Sometimes they quote from. You will see where they quote from. So now you can also subscribe to the site where they get all of these quotes from. So you can start from here and then branch out to other places where they keep an eye on technology. Oh, you're most welcome. Cool stuff, I think. All right, so getting back to the boring stuff. Let me see, what time is it now? Yeah, we got plenty of time. So let me give you a picture. Okay, so I'll give you this picture here. There's a positive charge here. There's a negative charge here. And we'll make a few transistors. Okay. The two transistors at the bottom, these are N transistors. Remember, N transistors do not have the little bubble thing. Okay? And the two transistors on the top are P transistors because they got a little bubble thing. Okay? And we are connecting the whole thing like this. A solid dot means it is not a wire that is flying over, and instead it is an actual connection. And then we'll label these points here. Let's say this one and this one are connected. And then this one, I will emphasize this is a flyover using this particular symbol. And we'll call this input 1. And then we'll call this input 2. And this is my output. Okay. So first of all, let me just kind of re-explain the diagram here. This is a circuit diagram. A solid dot like these means, the wires are actually connected. And if I have a symbol like this, it means it's a flyover. It means, this wire is not electrically connected to that wire. It's just that, it's flying over it. Are we okay so far with a junction versus a flyover? Okay. And we also have a few transistors. Let me kind of name the transistors because that makes it easier for the discussion. So we'll name this one Q1, Q2, Q3, and this is our Q4. Okay. So we have 4 transistors. Q1, Q2 are P transistors. Q3 and Q4 are N transistors. But wait, I have forgotten to label the little arrow thingy, right? So can somebody help me with the arrows? Remember, the arrows have to go from source to drain. With a P transistor, which end has to connect to a higher voltage? The source or the drain? The source of a P transistor is positive. The source of an N transistor is negative. So which way should I draw the arrow for Q1 and Q2? Down. That is correct. Okay, so we have down here, and then we have up here and up here. Because Q3 and Q4 are N transistors, so the source connects to the more negative side of things. So are we okay so far? Okay. If I really don't care about the intermediate voltages, okay, I just really care about what if things are all the way here and what if things are all the way over here, how many combinations do I get? This is the output, so it's not a part of what you can control. It's something you can observe but not control. In 1 and in 2 are things that you can control. You can give it a positive voltage or you can give it a negative voltage. Is that okay? So how many combinations do we get?
16.
Not 16. There are only 2 variables. In 1 is 1 variable. It can be positive or negative. In 2 is another variable. It can also be positive or negative. Yes?
Would it be 4 to the power of 2?
It's to the power of 2, but not 4 to the power of 2.
2 to the power of 2?
It's 2 to the power of 2. Okay? Oh, I misheard. I heard.
Which is 2
Oh,
to the power.
okay, thank you. I misheard as 4 to the power of 2. I didn't hear the words in between. You're correct. Okay. So you have in 1, in 2, and then we have out. So this is a truth table. In 1 can be positive. In 1 can be positive, while in 2 is positive or negative. In 1 can be negative when in 2 is positive or negative. Does that make sense? Does it make sense that this is enumerating all the possible ways we can configure this circuit as far as the inputs are concerned? Okay? So our job now is to say, well, what about the output, okay, for each case? So let's go ahead and try to work out this table. And I'm going to see if I can make a new layer. There we go. And I want to know which layer I'm on. Question is, am I on the new layer at this point? Oh, right here. Yep, I'm on the new layer now. The idea of using a layer is I can erase an entire layer and start from scratch. Okay. So let's try to work out the first one. I'm going to use a different color. Let's say blue here. Okay. So if you look at the first row, this is what we are working on at this point. The first row, we have positive here, and we have positive here. So just tell me, which transistor is open and which transistor is closed. Okay, or which one is connecting and which one is not connecting or disconnecting. Let's start with Q1. If there's a positive charge at the gate, this is a P transistor, is that going to turn on or turn off Q1? It would turn off Q1. Very good. So Q1 is not conducting. All right, so we'll just put a little cross here to say that it's not connecting. What about Q2? How is the gate, where is the gate of Q2 connected to? Into, which is also positive, right? So using the same argument, we also know that Q2 is also disconnecting. What about Q3? Q3 is an N transistor. What does a positive charge at the gate of an N transistor do? It turns it on, which means it connects, right? So Q3 is connecting. All right, so we are connecting here. What about Q4? Same thing, it also connects. All right. So now what we need to do is to track down starting from out and say, where is it connecting to? So we start off from out, and over here, well, these two nodes are the same. Do they have any way to connect to positive? Nope, because both paths to connect to positive are disconnected. Both of those transistors are open. Is that okay? What about the other way? Can we connect to negative from out? Yes, because even though we have to go through two transistors to connect from out to negative, both of those transistors are connecting. So we can actually have a connection. All right, so we have just figured out one answer here. It's negative. Are we doing okay so far with this? Yes? Okay. So can I erase all the blue stuff now? And remember, this is all being recorded. So just kind of mark the time. It is about 35, okay, 11:35. So mark the time if you want to kind of revisit the whole animation, okay? So I'm going to erase this entire layer. Go to delete layer. So it's kind of cool that we can do it this way. So I'll just write down the conclusion, output is negative in this case. And then we'll go ahead and make a new layer. And this time we'll use, let's try green. Okay. So the second row is now what we're dealing with. Okay. So the second row says N in 1 is a positive. Okay. So we'll label in 1 as positive, and in 2 is negative. Okay. So once again, we're going to work out the states of the transistors Is it connecting or is it not connecting? Isn't that the same thing as last time for Q1? Its gate is positive, which means it is connecting or not connecting? It's not connecting. Very good. Okay, so we know that this is not connecting. And we can track down where in one goes. It goes to Q3. It was connecting before. It is now also connecting. Is that okay? I'm just using the same reasoning as last time. But in2 has changed. In2 is now negative. So we track down where in2 is going. In2 goes to the gate of Q2. Q2 is a P transistor. What does a negative charge at the gate, what does that do to a P transistor? It turns it on or turns it off? It turns it on, which means it connects. Okay. All right. So we say that this is now connecting. But in2 also connects to the gate of Q4. So what does a negative charge at the gate do to an N transistor? It turns it off, right? So it's disconnected. So now we have this scenario. So now we are done analyzing the states of the transistors in terms of connecting and not connecting. Now we want to know the state of out. In other words, if I were to put a voltmeter at this point out, what is it going to experience? Well, let's track it down, right? So we track it down to here, and we ask, does it have a way to go to positive? Yes. Okay. But just to be safe, we also want to track down, does it have a path to negative? So it goes here, it goes here. It's connecting. Oh, it stops here, right? Because in order to go all the way to negative, you need to go through Q3 and Q4. Just having one of those two turning on or connecting is not enough for out to connect to negative. Is that okay? So if you put a voltmeter at out, it's going to give you what? Positive or negative? It'll give you positive. Very good. Okay. So I'm going to erase that layer again. Okay. And this time I write down positive here. What about the next row? Do you think I need to go through this next row here? It's a mirror image of what we saw earlier. In other words, what was on is now off. What was off is now on, right? So instead of having Q1, let's say with the other one, Q1 is off, Q2 is on. Now it's exactly the opposite. Q1 is on and Q2 is off. But they still have one path to positive. Sorry? It's the same result as far as out is concerned. Out is still connected to positive under this configuration. Are we convinced of that? Okay. So we'll write down this is also positive. And we have the last one to deal with. What if both in1 and in2 are both negative? It's still positive. Well, this one is just a much more extreme case of the other two, because now Q1 is on, Q2 is also on. We got two paths in parallel to connect to positive. We really only need one, but having two means, hey, it doesn't make it any better, but it's the same outcome. Before, we have at least one of Q3 or Q4 being off, and that's why we do not have a path to negative. This time, both of them are off. So it's the same outcome. We do not have a path to go to negative, but we have two paths to positive. So now we also know this is positive. Yes, go ahead.
Will you just point out where the sources and the drains would be? Because you had said that the source of P is positive, and so I would have expected opposite results for some reason.
Okay, sure. I can label the pins. So let me label the pins. This is G, this is S, this is D. G, S, D. G, S, D. G, S, D. Once you know the arrow, you know which side is the source and which side is the drain. the arrow indicates source to drain. Yep. It's okay. I mean, I can definitely label everything here. So, yeah, go ahead.
So the default state of a transistor the gate would be open and it would be not connected, right?
Say that one more time.
The default state of a transistor would mean that the gate would be open and it would not be connected?
Yeah. The state of a transistor depends on the voltage differential between the gate and the source.
Okay.
So if they are the same if they are the same, the transistor is off.
Okay.
In either case. I think there was another hand. Nope. Okay. All right. So at this point, we can just kind of ignore the picture, even though it explains how we got here. But we can ignore the picture for now. Instead, we'll focus on this little table here. Okay, so we'll focus on this little table. And I'm going to rewrite the table just down here a little bit. In 1, in 2, and out. But instead of looking at these things as physical quantities that you can actually visualize using a voltmeter, remember, you can actually build a circuit like this. Go find yourself 2 P transistors, 2 N transistors, hook it up to a power supply. This would be the positive end of a power supply. This is what we call the ground of a power supply, but you can look at it as negative. And then you can hook up one of these 2 inputs to either the positive end of the power supply or the ground of the power supply, and then put a voltmeter over here, and then you can measure whether out is the same as the positive voltage of the power supply, or it is measuring what we call ground, which is actually just called 0 volts, when you're using a voltmeter. But it's physical quantities that you can actually measure. These are things you can actually build, okay? So now we are taking one step back. We're abstracting the whole thing and just say, well, what if we don't want to look at it as positive voltage and negative voltage? What if I assign meanings, interpretation to these physical quantities? Okay? I say positive voltage is true and negative voltage is false. Do you know what I'm doing now? Yep, go ahead.
What is the graph or the thing called? Is it a chart?
It's a truth table. Yep, or logic gate table. Okay, so now I look at positive as true. Now in this class and also all of my other classes, I use 1 to represent true. Okay, so I hope you guys can get used to this. This is 1, 1. This is 1, 0, 0, 1, and 0, 0. So as far as the output is concerned, this is a false, and all of the other ones are true. Are we good so far? Does everybody understand how we got from the positive, negative table to the 1 and 0 table? And once again, 1 is true, 0 is false. So are we good so far? Okay? Yep, go ahead.
Backing up a little, can the gate ever be a more powerful transistor? Like, as if, can there be too much energy going through from the gate?
From the gate? There should be very little activity at the gate because it's not really, there's no current going from the gate to either the source or the drain. It's really the same thing as charging or discharging a capacitor. So you do have a little bit of current moving in this direction, depending on whether you're pushing the positive charge over here or pulling it away. But that amount of current should be very, very small. Okay, so we look at this chart here, and then I ask you, does it look like the truth table of one of the operators, Boolean operators, that you have learned in cisp310? Okay, so you got the actual answer. It is not and. Okay, because I need to point it out here and in a different color. Okay, if this were a 1 and these were zeros, then you guys would say, oh, out is really the same thing as in 1 and in 2, right? Because true and true is in red true. True and false is in red false. False and true is in red false, and false is in red false. So if we ended up with the red stuff, then a single conjunction or AND would just describe this whole circuit. Unfortunately, that's not what we have. We have exactly the opposite of what is appearing in red. But that's okay, because what can turn a false into a true and turn a true into a false? A simple negation, right? So that's why this is called a NAND gate, N-A-N-D. So let me just cross this out, scroll a little bit, and now I can express out is really the same thing as in one and in one and in two, but we negate the whole thing. Can everybody buy this? I'm using C++ syntax, by the way. Are we good? All right. So, yeah, go ahead. Because I'm establishing they are the same. It's not an assignment, it is equivalence. I'm establishing that this circuit is doing what a negation on top of a conjunction is going to do. Are we okay so far? Yes? I hope so. So this entire thing, now if you abstract this whole thing and put a big rectangle over it, okay, I'm going to put a big rectangle, okay, sort of a rectangle, with a notch over this whole thing. It's the implementation of a NAND 2 gate. The 2 simply means there are 2 inputs, okay? But it's a NAND gate, N-A-N-D, NAND gate. And I don't see anyone thinking that this is like a significant thing. It is significant because we just designed a circuit using real transistors, copper, wires, batteries, and whatnot to do a logical thing. But then you guys will say, yeah, but who uses a NAND gate? I mean, we know what is an OR, what is a NOT, what is an AND NAND is not one of those. So how is that useful?
And it is the gate that you can make every other gate out of.
Exactly. All of the other logical operators that you know, like a NOT, AND, and OR, they can all be done using NAND. So this is the one operator that you really need in programming. All of the other ones can be defined using this one. Okay? And no one is believing me. I can tell from your expression you are not believing me. So we'll leave it on next Monday to establish the equivalency between all the gates or all the logical operators that you guys are familiar with, NOT and OR, and I'll explain how they can all be done using NAND. We do have a lab activity. Yes?
Oh, I was just going to say, do we have classes today? Isn't it Labor Day?
Oh, right. Monday is Labor Day? Okay. So on Wednesday then. I don't keep track of holidays and that sort of thing. All right, so I'm going to release the lab activity now. So when we get to the lab, you just sign in and you can get started with the lab.
If I'm a waitlist person, should I still just go and sign in?
Say again?
If I'm a waitlist person, should I just go and still sign in?
Yes, you should be. You should have access to the class material already, so you should be able to do it.
I had a question about making sure to keep up on reading. I read through actually a bunch of those the things in Canvas, and it seems like I kind of read ahead, which I'm sure is not a big deal. But is there a way to understand what will be covered in class before we come?
It's really just kind of sequentially going forward.
Okay.
So right now
Is
we
it
are
generally like one document per class, like one module per
no depends on how. Yeah, some of those may take a few days, like more than a week or two to cover.
class? I see.
Yeah, so if you just kind of, if you're just ahead of the class, maybe by half a module or something like that, you're good.
Yeah, because if I hadn't have read that, I would have been even more lost than I am on this. So I feel like I got to do the reading ahead of time.
Okay, sure. Yep.
I just wanted to ask, are we doing permission numbers today for those who need to add the class?
Yeah, I can do permission numbers maybe later, but you still have access to the lab activity today. But I will send you the permission number. I can add everybody to the class.
Okay, thank you.
Yep.
That's what I want to know.
Okay.
Question, Professor?
Hmm?
So for the direction arrow for the current, or for the N transistor and the P transistor, is it always going to be the same, or does it switch depending on the source of it?
Say that one more time?
So for the direction for the
Yeah.
voltage,
It's just a notation. Yes, but in terms of notation, they are always going from source to drain.
and so if the source was down here, so it would just switch directions based on the source and the drain.
Yes, because the source of an N connects to negative, and the source of a P connects to positive.
Okay, so all right, okay, so, okay. Thank you.
Mm-hmm.
That's the wrong time, huh?
Yeah,
Okay. We'll give you an excuse.
Hi,
Like,
Becky.
That's the wrong time.
Way wrong.
Yeah, way wrong time. Now I can't watch that.
Yeah, I have to watch my own Fitbit, which